said, I'll keep you posted on test stuff as it becomes available. But today we are going to continue with what we've been doing. So let's just get to it. So constant rate of change and linear functions. That's where we're at. So here's as many ways as I could come up with to talk about this once more in summary. So if y varies with a constant rate of change with respect to x, changes in y are proportional to changes in x. Every change in y is a constant multiple of its corresponding change in x. And we write that as delta y equals k delta x. Every delta y has the same relative size to its corresponding delta x. Right? And so we represent that using the quotient. When we talk about relative size, we're talking about a quotient. Okay? Whenever x changes by 1, y changes by k. Or k is the change in y per unit change of x. Okay, so those are two equivalent ways of saying the same thing. Y always changes k times as fast as x changes. Equal changes in x result in consistent changes in y. X and y are in a linear relationship with a constant slope. Okay. Is anything on this list jarring or something that you would like to take a moment to review? This is what we've done, right? And today we're going to really focus on bullet point 7, okay? So at the risk of being redundant because it's that important, okay? Two changing quantities vary together at a constant rate if equal changes in one quantity result in consistent changes of the other quantity. I'm going to skip saying those out loud fast because I want to actually give you the visual to go with this. Okay? So what does this mean? If we look at equal changes in x, then the corresponding changes in y are going to be the same. Okay? That's what I mean when I say consistent changes of the other quantity with changes in one quantity. Okay? It also, constant rate of change, we could also express this as saying the change in one quantity is a constant multiple of the corresponding change in the other quantity. So what's a visual to go with that? Well, I've got a whole bunch of changes in y that can be produced by multiplying the changes in x by the same amount. Okay? How is this? Groovy? Yeah? A little bit? Okay. And so again, we can represent this idea, this constant rate of change relationship with delta y equals k times delta x. That formula is exactly expressing that the change in one quantity, y, is a constant multiple, k, times the change in the other quantity, x. Okay? That's exactly what we're saying in this sentence. And then another way that we've been expressing this is to say that the relative size of corresponding changes of the quantities is constant. So again, what does it mean to say the relative size of corresponding changes? What kind of thing am I talking about? I heard it. A quotient, right? So when we talk about relative size of changes in y and changes in x, we're talking about quotients. So if I look at the quotient of the relative size of delta y1 to delta x1, that should be the same as the relative size of delta y2 to delta x2, and so on, right? So for any change in y relative to a corresponding change in x, that relative size should be a constant, which we call k. And that is the constant rate of change of y with respect to x. Okay. Can you guys help me out and actually estimate what is k in this graph? So what is the relative size of the changes in y with respect to the changes in x? Okay. Who wants to take it away? You had your hand up. Okay. Okay, so about a half, and how are you thinking about that? What are you comparing? Awesome. Okay, that's great. That's what I wanted to hear. Um, oh, we went back way too far. Hold on. Okay, so that yes. Ooh, blah. We're just not going to go there. Okay, so now let's actually see this in action. Okay, so I've got a scenario again. We're not in Vegas anymore, but that's okay. Not all life is a party. So we've got two painters. They started painting their respective houses, right? So they started in the morning. One painter painted 250 square feet. The other painter painted 400 square feet. Then they took a lunch break, okay? So this is where we're at. Now, with that scenario in mind, how might I use these bars as they're presented to label the scenario? What should I label? I don't know. The purple bar. Could I get Aaron? The top bar is painter 2. So painter 2 is a person. Okay, so the quantity being represented by the blue bar is not painter 2, right? Because painter 2 is not a quantity. Painter 2 is a person. Okay, but the blue bar could represent the number of square feet, for instance, that painter 2 painted, right? So this is going to be a number of square feet painted by painter 2, right? And so I guess you picked painter 2 because he had painted more? Okay, and that bar is bigger. Okay, so that's reasonable. So then the purple bar would be, yep, the number of square feet painted by painter 1. Okay, now, okay, so that's where we're at right now. They took their lunch break, they came back. They start painting again, okay? Now, let's say that after lunch break, painter 1 paints another 200 square feet. So I'm going to make that happen. Okay, so there's one. Oh, that's not it. Hold on. Oh, it's so close. I don't know. I didn't eat the appropriate breakfast, so I'm a little shaky today. Okay, so painter 1 came back from lunch. Painter 2 came back from lunch. They both started painting, and I'm telling you that painter 1 painted another 200 square feet. So if I were to label what's going on here, well, what have I done, first of all? What do you notice about the bar diagram? I did something a little special to it that we haven't seen before. Yeah. Okay. Okay. Yeah. So I've got like bolded lines for the initial amount that they painted before lunchtime, and then I've got the skinny lines showing the change, right? So this skinny line in purple is representing how much? 200. So, oops. Love technology. Love it. Love it. Come back. Okay. So what do I want to say? So at the end of lunchtime, come on. This guy had painted 250, right? Or at the beginning, when lunch started, 250 square feet had been painted. And then I said that after lunch, he came back and painted another 200 square feet, right? So this amount right here is 200 square feet, which makes this end value 450, right? Okay. About where did we land up here? So this was at 400. Can you see the vertical lines? I've got vertical lines, these things. So what, every 2 is 100? So about where did we land over here? So that's 5, 6, 650. Okay. So my question to you is, if we were to call the number of square feet painted by painter 2 y, and the number of square feet painted by painter 1 x, are x and y in a proportional relationship? Okay. Yes. Can't tell yet. Okay. You want to say something? Okay. Mm-hmm. Okay, so let's actually make a table so that we can see what's going on. So if I wanted to compare relative sizes of y to x, I can keep track of values, right? So I've got x values and y values. At the start of lunch, right, we've got 250 square feet painted by painter 1 and 400 square feet painted by painter 2. And then after they get to work in the afternoon, I've got 450 here and 650 here, right? What would the mathematical sentence be to say that x and y are in a proportional relationship? What does that mean? So I'm talking about the actual amount of square feet painted right now. Mm-hmm.
So the amount of square feet painted by painter 1 and painter 2, the relative size of the amount of square feet would be constant?
Exactly. Okay, so in order to say that x and y are in a proportional relationship, I would actually need the relative size of y to x to be a constant, right? So my question is, can I write this type of relationship? You want to take a second to talk to your neighbor and answer that question? All right, you got some answers for me? Yeah. Okay, so I think what I heard was that the values that are in this table of x and y don't actually satisfy this relationship, right, for a single value of k. So like if you were to actually rearrange, this formula that I'm asking you about, an equivalent form would be to say that y over x should equal k, correct? And so if you take these values in our table, 400 over 250 is not the same as 650 over 450, right? So we don't get this relationship, right? And it just takes testing those two distinct points, if you will, to figure that out. However, I do hear people talking about changes. So, okay, so if I concentrate on the changes now, could I maybe make another table and represent what's going on? Do I have enough with what's written to create a table to sort of really convince myself that I've got a constant rate of change relationship? Yeah?
You do if you want to like create a third point.
Ah.
But if you wanted like an actual true statement, you would like need to be given that third point to determine.
So there is information missing, right? At the moment, if I wanted to create a table recording values of delta x and delta y, how many changes do I have to consider in my diagram so far? I only have one, right? Because I only changed from 250 to 450 for painter 1. So that's a change of how much? 200. And then for painter 2, how much did it change by in the corresponding 250, right? If that's all I have, I can't say anything yet, right? Because obviously if I take the quotient of these two quantities, I will get a constant. That's cool. Okay, but that doesn't give me enough information. So I need to actually, to have another, say, let's say that the painters both kept painting their respective houses for another amount of time, and painter 1 ended up painting another 300 square feet in his house. Okay, so now painter 1 is out to where? So we're at 750 now. Okay, about where is painter 2? So this was 650, 750, 850, 950, 1,000, 25. Okay. So all right. So what can I put up here now? So if I concentrate on this change, right, the second burst of energy he had in the afternoon, that was a change in 300. And the corresponding change for painter 2 is 375. Okay. Are those the only change relationships we have represented? Yeah, you could talk about the entire afternoon, right? How much of a change for painter 1 in the afternoon? 500. And for painter 2? 625. Okay. So now take all three of these and tell me what is the value of delta y over delta k, or delta x. So 250 over 200 is 1.25. What's 375 divided by 300? 1.25. 625 divided by 500? Oh my goodness. Okay, so the fact that this quotient, changes in y over changes in x, no matter which changes in x and corresponding changes in y I look at, always produces the same constant, that's how we know that we have a constant rate of change scenario. Okay, so this 125 is our our constant rate of change. Okay? Of y with respect to x. Okay. Now, okay, so there's the bar diagram version. Let's take this up a notch. So if I, flip the blue bar so that it meets the end of the purple bar, then I can actually keep track. Whoops, wrong way. Oh, it does it so fast. Okay, then I can actually keep track of what's going on. So at the beginning, right, this is where we're at. The painter 1 had painted 250, painter 2 had painted 400 square feet. And then that changes, right, in the afternoon. So if we wanted to, we could actually put our vapor trail back on it, right, and keep track of all of the points describing the scenario as the painter's paint, right? And so when you do that, you get a line, right? A collection of points in a linear relationship. Mm-hmm. Well, so the 250 and 400 square feet are recorded right here, but you're asking, like, why don't I have a line going? It's just a matter of when you start paying attention to the scenario. That's all it is. It could be the case that painter 1 was painting really, really fast compared to painter 2, and then slowed down. And so, like, we don't actually know the relationship between how much painter 1 painted compared to painter 2 before painter 1 had painted 250 square feet and painter 2 had painted 400 square feet. We just don't know what that relationship looks like. It might not have been in a constant rate of change relationship. Okay. So that's why our graph starts where it does, because this is all the information that was given to us. Does that make sense? It's a really relevant question. But this is as much as we can say based on the information given. Okay. So now let's say I want to represent everything that we've been talking about just now on the graph. Okay. So if I wanted to, again, so we had this point was 250, 400, right? And then I think we had, what was it, 450, 650? So here was another one of the points that we talked about in our bar diagram, 450, 650. So if I wanted to represent visually, what would I do? Represent the constant rate of change relationship visually? Mm-hmm. Mm-hmm. Ooh. Hold on. Gonna work it out. Sorry, guys. Uh-oh. Okay, it'll be faster if I just start over. And okay. So from here to here, right, we can create our triangle saying, okay, so this delta x was 200 and the corresponding delta y was 250. Okay. But in terms of all of the work that we had done on the previous bar diagram visuals, right? We could also keep track of the fact that, okay, so this 250 comes from doing 1.25 times the change in x, right? So, okay, so now let me ask this question. So let's pretend that I didn't know the actual y value here. If I wanted to come up with that value, what would I do? Hold on, I lost my, oh no, I lost my slider. Yeah, I can't do that at the moment because I'm in this other program. So here's what I'm going to do. Close it. Yay. Okay, so if I wanted to know the y value, right, at when x is 450, then what can I do? Using the relative size relationship that we've talked about. So why did things change so much? Ah, shoot, guys. I'm sorry. So technical difficulties, tell you what, rather than annoy us all, let's move forward because I have all of this stuff sort of in another place. Okay. It's not in context, but it'll get the meaning across. So this is what I wanted to get at, right? So the meaning of slope. So when we talk about a constant rate of change relationship, as in the Painter scenario, we can compute, or we give this label slope when we talk about a line to the value of the constant rate of change. So slope is calculated by doing what? So I just said what it is, right? So slope is the value of the constant rate of change. So how do we compute constant rate of change? Change in y. Oh my gosh. Okay, hold on. You weren't supposed to go yet. Change in y over change in x, right? So that's how we compute slope. And then when I look at this picture here, I already gave it away. How many changes in x and y exist here in this picture? Infinitely many, right? Just because I've drawn one specific triangle to represent changes in y and changes in x doesn't mean that those are the only ones there, right? So we've got as many changes in y and changes in x as your heart could dream of represented in this image, okay? Okay, so a function that has a constant rate of change that passes through a point AB. So in this picture, AB is the highlighted point. Okay. What if I want to get at its definition? Okay, so that's what my goal is at the moment. What do I need to know in order to give the definition of this function? Well, I need to know the point. I need to know the slope, right? And I can say, all right, so this point represents when the x value is a, when the y value is b, and I end up with this formula. Okay, but where did this actually come from? So let's think about that for a second. So if I were to take any other ordered pair, right, x comma y on this line, right, satisfying this relationship, then I could really think of it as, so like my new y value, right, is going to equal whatever my old y value is plus the change in y. Does that make sense? So in this case, my new y value is just y. My old y value was b. And then how do I get a change in y if I'm in a constant rate of change relationship? How do I get change in y in a constant rate of change relationship? So I can't just say new y minus old y, right? Because that's not giving me new information. That's just rearranging the equation I wrote down, okay? But I know something special about the y's and x's in this relationship. They're in a constant rate of change relationship. As soon as I say that, what can you tell me about delta y? What'd you say? Nothing. This was on your test yesterday. I'm getting a little nervous about the scores I'm going to see. Okay. What does it mean? What can I say that delta y equals? K delta x. Oh my God, thank you. Okay. So, okay, and we just said that the k, right, the value of the constant rate of change is the slope, right? So then you get plus m times, and then in this case, what's the change in x? To get from this point to this point, what do you have to do? Right, you've got, so the new x value, right, which was, so this is my delta x, and my new x value is x, my old x value is a. So change in x is x minus a. Okay? That's where this comes from. Okay? So if you've been one of those people who just absolutely loved y equals mx plus b, here's my argument for ditching it, right? If we look at this point slope formula, that's the name given to this version of the equation of a line, everything here has a meaning, right? This y value is representing a new y value that I might care about. This b is the old y value. This m comes from thinking about the relative size of changes in y to changes in x, and that gives us, you know, and then we can talk about the actual change in x. So this is where this comes from, okay? And there you can see it again, a little bit more highlighted, okay? All right, so then here is what might have been on your brain for a while now, actually. What does this all have to do with calculus? Okay, so in calculus, the idea of a series of small equal changes in x is important. And that's going to become really obvious in a very short amount of time. Okay, for now, I'm going to ask you to take my word on it. But so what do I mean when I say a series of small changes, equal changes in x? I mean what I have drawn in this picture. So in this picture, I've got a graph that has repeated intervals with size of x being 0.1 and corresponding changes in y. Okay, so my very small changes in x, a series of them, and then the corresponding changes in y. So I want you to take a second to describe the covariation of y and x as represented by this graph. Okay, so take a second, talk to your neighbor. Question? Well, so covariation refers to the way that they change something. All right, what you got for me? So when I use this word covariation, what am I referring to? How quantities change together, right? So give it to me. How are these quantities changing together? Yeah. Okay, so as x increases, y decreases at a constant rate. Can we be more specific? That's yes. Yes. Okay. Can we be even more specific in terms of sizes of changes? What is that constant rate? How might we figure it out? Yeah. Mm-hmm. Looks like it, yeah. So for every increase in x by 0.1, y decreases by 0.2, right? Great. Okay, so taking this and combining it with, was it David? David? Yeah, what David said, we could actually compute what this constant rate of change is, right? How would I do that? How do I find the constant rate of change? I actually can compute it, right? Change in y over change in x. So I just found out that y decreases by 0.2, right? So I can encode the decrease using a negative, so negative 0.2 for every 0.1 change in x. Okay, so what's the slope of my line? Negative 2. What's the relative size of changes in y with respect to changes in x? Negative 2. Okay. That looks like it disturbed you.
I thought you said negative 2. Is it negative 0.2? Or did I miss something?
No, it's just negative 2. If you divide 0.2 by 0.1.
Sorry.
Yep. Okay. Cool beans? Cool beans. Your turn. Okay. Rather than giving you the graph, I'm now giving you the scenarios. Okay. So for each of the set of criteria below, model the covariation of x and y as follows. I want you to sketch a series of steps, just as I had drawn in the previous, so, various step sizes, to create individual points and then sketch the curve. Graph. I said sketch the graph. Starting from x equals negative 0.8, y equals 0.1, a change in x of 0.2 results in a change of y of 0.6. Subsequent changes of x of 0.2 result in positive changes in y, which decrease from one to the next. I just noticed that when I typed this, bad things happened. So in the parentheses, this should be delta x equals 0.2. Okay. Right, because we're talking about subsequent changes of x of 0.2. That means delta x equals 0.2. Okay, so take a stab at creating a graph to represent this situation. Interpret it, talk to a neighbor if you want to, but work it out. So are you guys still thinking about A? Have you thought about B? Did you decide to start with B, move backwards to A? Where are we at? What are we thinking about? Yeah? I'd like to know what you guys are thinking about, yeah.
A, I'm thinking that like it looks like it starts constant, but then it increases at a decreasing rate.
Okay. So you're thinking about A. Okay, I like it. That's an answer to my question. So if you wanted to start creating steps of individual points, the most logical place to start would be to start with plotting the point that they gave you, right? Negative 0.8, comma 0.1, right? So we've got this point right here. And then what does it say happens? From here, if I do what happens? Okay, so if I increase x by 0.2, so this is a delta x of 0.2, then the subsequent result in positive, what happens? The result in a change of y of 0.6, right? So my corresponding change in y will be 0.6. So that lands me at a new point, right? What's the new point? Negative 0.6, 0.7, okay? So so that's cool. But then what? What do they say happens after that? Subsequent changes of x result in positive changes in y, which decrease from one to the next. So the next change in x of 0.2, right, is going to result in a change in y that's positive, but smaller than 0.6. Okay, so it doesn't say by how much, so I don't know. I didn't leave myself very much room, so how about it only increases by 0.1? Okay. Right, so this could be the next point at negative 0.5, comma 0.8, right? And then if I change by delta x, if I let that be 0.2 again, then my next change in y is going to have to again be positive, but now it's going to have to be even less, right? It's going to have to be less than 0.1. So then, is this covariation just happening in a constant rate of change relationship? No, right? That's not what is being described here. So one possibility for what my graph might look like, it could be curved all the way through, right? Or it could have just been like line here, and then another line, right? There's lots of possibilities. We don't know exactly what the curve looks like, okay? But we do know sort of a general outline, okay? What about B? How does B differ? So it says I start at negative 0.5, negative 0.5, and a change in x of 0.25 results in a positive change of y of 0.1. So if I do positive change in x of 0.25, I get a change in y of 0.1, okay? And then what? It says all subsequent changes, all subsequent changes of x of 0.25 result in a change of y of 0.1. That stays the same, right? So if the change in y is always the same relative to the change in x, then we are in fact describing what kind of relationship? the constant rate of change relationship. And so if I were to keep creating steps, right, I'd end up with some sort of linear, it doesn't actually go through the origin, but some sort of linear graph, okay? All right, so I've added stuff to your Monday assignment, so you should keep track of the updates on Blackboard. Yeah, have a great weekend.